Newton's method. You know, I'm really bad for claiming lessons are my favorite lesson. You notice that? All of a sudden I go, oh no, this one's my favorite lesson. And I'm not lying when it's happening. Maybe I'm not thinking enough about what other lessons are out there. I sort of forget. I'm like, no, this one's my favorite. This is one of my favorites. And because it closes a gap in what's going on that has been going on for a while, maybe all the way back to grade 10. All the way back in grade 10 is, well, what happens if it doesn't factor? Grade 10, we had the answer, quadratic formula. Then we sort of leave that on the shelf. We just act like everything factors for a long time, all the way through regular calculus. We just act like everything will just factor. But maybe you've done enough science in other courses now to go, wait a minute, there's no reason that these numbers have to be nice. In math class, they're giving us numbers like 3 and 5 and -2, maybe 5 halves, ooh, you know? But the actual functions that are out there have these crazy decimals to them. How in the world is it possible that those things would factor? And the answer is they don't. Factoring is a very useful tool, and it helps us a lot in a lot of stuff that's going on. It's been fundamental to our understanding of calculus and where the stuff in calculus comes from. But as we journey into actual applications, what are the chances these things actually factor? And the answer is extremely low. So what then? Well, there's a million methods out there. There's a million methods out there to find zeros or to find values of functions when they won't factor. And Newton's method is one of those. It is not the best of those. It is the simplest, though, because I'm going to tell you, the only weapons I'm going to use today is the function, its derivative, and a really good guess. You go, well, how am I going to get the really good guess? And I'm going to warm up with that right here and show you where the really good guess comes from, because that's actually the least of our problems, is getting the really good guess. Watch. Newton's method gives us a way to find zeros of a function. That is, it is used to solve equations of the form f at x equals 0. This method is especially useful when we are unable to find zeros using any other method, such as factoring or the quadratic formula. For example, Newton's method can be used to find the zeros of a quintic. That's degree 5, by the way. Function that doesn't factor since no quintic formula exists. Okay, so actually, there is past a quadratic formula, there is a cubic formula, but it's so unbelievably difficult to use. Well, not difficult. It's not difficult, actually. It's just long. You know, the one you're used to is x equals -b plus or minus the square root of b squared minus 4ac all over 2a. That's the quadratic formula. The cubic formula is like, it's like a full page wide, and each of those numbers in there is its own little calculation before you can use the main one. It's crazy. And the quartic one is unbelievably nuts. Like, it's completely insane. But they found it. Mathematicians have found a nice quartic formula that can be used. Quintic, they haven't found one. And I forget if this is the one. I think quintic's the one they've proved there can't be one. You know, but it gets to the point where it's like, okay, these formulas aren't going to work all the time, and we're going to need a new strategy. How is this all coming up? Let me rewind a little bit and talk about how this is coming up. I'm going to make up a very simple function, say f at x equals x cubed plus x squared plus x minus 2. Say that came up in the homework all the way back in advanced functions. It says find the zeros. So you proceed, and it doesn't look too bad. I've chosen one that actually looks very nice, you know, very controlled numbers. And so you let p at x equal x cubed plus x squared plus x minus 2, and you start your factoring procedure, assuming that it's going to factor. And you go p at 1. And what do I get here? 1 plus 1 plus 1 minus 2, I get 1. So that didn't work out. I go p at -1. That'd be -1 plus 1 is 0. That's good. Minus 1 is -1 minus 2 is -3. So that didn't work out either. Then I try p at 2. Because maybe I remember that the only things that can work are things that divide into the 2. You know, those are the only possibilities that can even potentially work. And I get 8, 12, 14. I get 12. When I do p at -2, I get -8 plus 4 is -4. Minus 2 is -6. I get like a -8 there. And then I stop. That's the end of our skills at this moment. This is why I said this lesson's perfect. It fills a hole in that. It's like, well, what happens if it doesn't factor? Because it seems like we have no skills available at all. And what I said is in this lesson, I'm going to, with a good guess, the function and the derivative, that'll be enough for us to narrow down zeros. Okay? How do we get the good guess? Well, actually, if I just sort of graph these points, I can come up with a great guess. There's more information here than meets the eye. We were looking for a 0, but there was a lot more information here than met the eye. And without even a piece of graph paper, I don't even need a fancy graph of this to see what's happening. So I did 1, negative 1, 1, 2, 2. Okay, good. So I did p at 1 is about 1. It's about there. P at negative 1 is negative 3. It's about down here somewhere. P at 2 is like 12, so it's way up here. And P at negative 2 is like negative 8, so it's down there. Can you see where the 0 has to be? I'm just going to fill it in green here. Somewhere between here and here. That's intermediate value theorem, actually. Intermediate value theorem says if you're down here at negative 1 and you're up here at positive 1, somewhere in between you've got to get a 0. And we knew we were going to get a 0 because cubic, way back when we talked about cubics going, cubics have to have zeros. Eventually, it's got to go through the x-axis and give us a 0. And now I've got a pretty good guess. You know, I'm guessing about 0.5. Is that a great guess? Well, I don't know. I'll find out. I'll sub in 0.5 and I'll see what happens. That's the start of the method. Get a good guess, and it won't be hard to get a good guess. I'm telling you, it will not be hard to get a decent guess. You sub in a couple of numbers just like you would with factoring. You'll probably have that guess ready to go anyways because you tried to factor it. You'll probably have a good guess ready to rock and roll. Okay? On to Newton's method. Here's the big idea. Make a reasonable initial approximation of the 0 you are trying to find using substitution or a graph if it's available. You'll probably have this guess ready to rock and roll anyways. Once you have a reasonable guess, use your approximation to determine the curve's y value, which won't be 0 because you found out it's not a 0, and the slope. Find the tangent slope, and the tangent slope will give you a guide of where to look for that actual 0. What I mean by that is, if this slope is very large, it'll tell you, don't move over very much. Just look a little bit to the left, and you'll find your 0. If you're worried about negative slopes, don't worry. It takes care of all that. It's fine to just look at this picture and think it through on that picture, because negative slopes will take care of themselves. Trust me on that. It'll be fine. Now, if this slope wasn't as large as you see here, if it was much more shallow like this, it would tell you to move over more to look for your 0. You know, the tangent slope is helping get back to that 0. In fact, what it's actually doing is drawing a line right there and using that line to go, here, look there. That'll be a better estimate of the 0. Will it be perfect? Well, no, I think you can see in the pink line there. No, it's not perfect, but it's way better. Now, if you're thinking, won't this take forever? No, it's really good. It's really good about how fast it works. It works shockingly fast because as you get closer to that 0, the slope gets more shallow or it gets steeper. Well, it works. It works so good. You'll see. Using your approximation, determine where the curve's tangent slope hits the x-axis and then go, well, there's a better approximation where the tangent slope hits the axis. The tangent slope is giving you a guide of where to look. This value will be better. And maybe it doesn't matter about the whole faster thing. As long as it's better, we'll get there. Yeah? Repeat the step 2 as much as needed until you get as good an approximation as you want. You're like, well, how do I know I'm getting close? It'll work just like the tables back in advanced functions where you go, oh, it settles into a value. You know, if it stops changing very much, you know you've got a good value. You'll see. I'm going to do an example. Now, you could carry this process out. You could actually find the whole equation, but you don't need to. Newton's method gives a very good approximation. You're basically using the tangent line to find the next estimation. So there's a nice formula for it. In general, well, here's the whole approximation. Don't let the symbols intimidate you. Let me say this in words first before you worry about the symbology here. Take your guess. Yes? Subtract the y value divided by the derivative there, and you'll have your new guess. That's as simple as what's going on here. All you need is your guess, the y value there, and the slope there. You're making your guess better by subtracting off the y value divided by the slope. You'll see exactly how that plays out in a minute. So now, this is just your next guess. And again, if these xn's are driving you crazy, don't even worry about that. When I write it out, you're going to be like, oh, I see what the xn's mean. It's like, come back to this formula later when you understand it better. Trust me when I tell you, all that's going on is take your guess and make it better by subtracting the y value over the derivative. And get your calculator ready, by the way, because I'm going to show you a very cute shortcut in your calculator. Can you see how this formula is derived from the diagram? Let's go look at the diagram. When you make your guess, your y value is going to be incorrect. It's not going to be 0. How much is it going to be off? It's going to be off by this amount, this y value. And we're going to adjust it by dividing that y value by the derivative there and saying, how much is the slope changing? And that slope will tell us how much to move over. That's how it comes from the diagram. Oh, and here's the complicated diagram. I'll come back to this at the end, maybe. All we're saying is to get the new y value, start with your x value and subtract off this much, which will be the y value divided by the derivative. So here's the procedure, even though this formula tells you the procedure. Guess a first approximation to the solution. Use the first approximation to get a second, and the second to get a third, and a third to get a fourth. And if you're worried this is going to take forever, it just doesn't. It goes very, very quickly. It only takes a few approximations, and we'll do very, very well. Well, let's not wait any longer. Let's get right into one. Got to open that up here and get as much space as I can. Consider the function x cubed plus 2x equals 1. A lot like the example I did, slightly different in that it's very simple looking, but it's not easy to find the zeros without Newton's method. Once we have Newton's method, life's pretty straightforward here. What is the maximum number of solutions a cubic equation could have? 3. The most you can get is 3 answers. The reason that is if this could factor, you could get 3 different factors because it's a cubic. You could have 3 different sets of brackets. Rewrite the equation in the form appropriate for the use of Newton's method. That is, we need a function that we're finding the zeros of. So I'm going to let f at x equal x cubed plus 2x minus 1. I've brought that minus 1 over so I can let f at x equals 0. Yeah? I've made that all on one side, so it's x cubed plus 2x minus 1. I've just moved that one over, and I want to know when that function equals 0. That's what Newton's method is designed to do, find zeros of functions. So I almost threw that in at the start of the lesson and said, well, it's not just zeros I'm looking for, actually. I can find any value of a function. If they want me to find f at x equals 9, no problem. I bring the 9 over and I find the 0 of that function. We were doing that the whole time with factoring anyways. When we wanted to factor something, we brought it all to one side and then factored. So here's the function I want to find the 0 of. Explain why the initial approximation of 0.5 is a suitable one for using Newton's method. And it's similar to the opening example I did. It's so similar, it's like, why didn't you just do it here? Well, I wanted to warm up first. I wanted to see what I was doing. That is, if I go f at 1 here, I get 1 cubed is 1, plus 2 is 2. I get 2. If I go f at negative 1 here, I get negative 1 plus negative 2 is negative 3. I get negative 4. And so I notice that 1 and negative 1 are not zeros, but one's positive and one's negative. And the mean value theorem is just jumping up and down going, I can help, I can help. Yeah? If you're going to go from negative to positive, the mean value theorem says somewhere in between, you've got to be able to find a 0. So, I mean, if you're with it at all, you'll probably then check, well, let me check 0. And f at 0 is negative 1. And so a little tiny graph, not even a quality graph of this, will really help. It tells me that f at 1 is around 2. F at 0 is like negative 1. And f at negative 1 is like negative 4. And do you see how they sort of came up with 0.5 as a decent first guess? Is it a great first guess? Well, no, I can sort of see it's not going to be perfect, but it's a good first guess. And what I'll write is somewhere between 0 and 1 is a good first guess. So why not 0.5? You're like, well, no, I would start with 0.25. I think that's better. Good. You got your good first guess. Whatever you like. 0.5 is what I'm going to start with. Use Newton's method with an initial approximation of x1 equals 0.5 to find the third approximation of one of the solutions. One of the solutions. Remember, there could be 3 out there. We're only working on one of them right now. How do we get the other ones? Well, there's lots of ways to get the other ones after we have one. We'll focus on getting one. If we can get one, we'll be in good shape. Okay, so x1 equals 0.5. And I got my formula for xn plus 1. Let's take a look at this thing now because it's a little mysterious, the symbology. It says xn plus 1 equals xn minus f at xn over f prime at xn. And what I'm going to do next, hopefully, we'll show off the symbology here. We'll show off the method here. And we'll also show off why we use this method. I think everything happens here. So I'm going to let n equals 1. And if that seems like a completely arbitrary move that I've just pulled out of thin air, that's okay right now, because partway through me taking n equals 1 and putting it into Newton's method formula here, you're going to go, oh, I see why you chose 1, and now I'll know what n value to choose. Yeah, you'll know. So I'm going to put n equals 1 in here, and so I get x at 1 plus 1 equals x at 1 minus f at x1 over f prime at x1. I just put n equals 1 all the way through there, and I get this beautiful formula. And I say beautiful because it might really show off the power of this formula. It says to find x2, take x1 and subtract f at x1 over f prime at x1. I hope that's demystified a little bit, the symbology here. If you want to find the second approximation, make n equals 1, and it says the second approximation says take the first approximation and subtract the y value over the slope. That'll give us our next good approximation. All I want you to understand at that point is the demystification of the symbology here. If you just put in some n value, you'll be able to see what this formula is really talking about. Now, why is that formula what it is? Well, maybe we have to see a little bit more to see why it's like that. So I need 2 things. I need f at x, and I need f prime at x. F at x is x cubed plus 2x minus 1. And f prime at x is 3x squared plus 2. So to get the second approximation, I take the first approximation, and then I go take that first approximation cubed plus 2 times that first approximation minus 1 all over 3 times that first approximation plus 2. Now, if you think I've made it more complicated by the way I've subbed that in there, I'm up to something. I'm up to something shockingly cool. I hope you got your calculator out. If not, I'm going to do it on the screen, and you can see what your calculator can do. And it doesn't matter if you got the fancy Casio one, or any calculator is going to do what I'm going to show here in a minute. So, if I want the second approximation, take the first approximation and subtract the function over the derivative. So the function will be take my x1 and sub it into each one of those, and put that over the derivative subbed in. Let me actually then go, okay, but x1 equals 0.5. I actually know it's 0.5. You're like, since you knew it was 0.5, did you have to write it out like that? No, actually you didn't. But to do the cool thing I want to do, I really want a formula for it here or something. Okay. So x2 equals take the 0.5, which wasn't right. It doesn't give me the right answer. You're like, how do you know it doesn't give you the right answer? Watch, I'll show you in just a second why it doesn't give you the right answer. And then in the numerator, I go 0.5 cubed plus 2 times 0.5 minus 1. The denominator is 3 times 0.5 squared plus 2. So x2 equals, where's my calculator? Here we go. 0.5 minus fraction button, oh, fraction button. I'm trying to convince the grade 11s, get a calculator with the fraction button. Not just the regular fraction button, the one that shows the fraction. Just makes your life so easy, much easier here. 0.5 power 3 plus 2 times 0.5 minus 1. Incidentally, if that numerator is 0, because this actually was the 0, 0.5 actually gave the 0, then I'll just get 0 up there, and the party will be over. Yeah? That's why I can assume it's not the actual answer, because if it is, it's all going to work out here. Denominator, divide by the derivative. 3 times 0.5 squared plus 2. Basically what we're doing is saying, take the y value, which will be wrong, it won't be 0, and divide by the derivative. That'll tell us how much to move over to get my good answer. Yes? Equals. Second approximation. Oh my. 0.45454545. My calculator, 2, 3, has 1, 2, 3, 4, 5 sets of 4 5s. 2, okay. Listen, if your calculator doesn't have all of those digits, or if you round off, everything still works out here. It just might take you more time. Okay? Is that the right answer? No. It's a better approximation. 0.5 wasn't good. In fact, my diagram might have been enough to say, you know, I really think it's going to be left of that. Yeah? But this immediately narrows us down to a much better solution. This said find the third approximation. Go to x3. Now check this out. x3, if you've been asleep the whole lesson, or if you're falling asleep right now, now's the moment to tune in, because Newton's approximation goes from this weird thing I'm showing to like, oh, with the calculator, this is cool now. To get the third approximation, I have to let n equals 2. Sorry, I should write that in there. I've done so many of these over the years that I don't even think about the n value anymore. But it's the n value of 2 back here. X at 2 plus 1 will give me x3. Then I do take the second approximation, subtract f at x2 minus f prime at x2. And if your brain started going, oh no, here we go. With this, subbing this in. Look what we're going to have to do here. We're going to have to take 0.45, and I have to sub it into here, which would be 0.45 squared plus 2 times 0. Don't write 0.45. Mr. Todd, don't write 0.5. 2 times 0.45 minus 1 all over 3 times 0.45. Don't write 0.45. Write x2. Just let me stop there for a second, because this formula I've made is really, really cool. With this 0.4545454545, that's what I'm going to have to type in my calculator. Get ready. This is what you should type in. I'm not going to do it. I should type in 0.4545454545, subtract 0.4545454545 squared, plus 2 times 0.0545454545 minus 1 over 3 times 0.4545 squared plus 2. I'm going to have to, every time I see that x2, I'm going to have to write 0.45454545. Scary. Question? That's a cubed right there. Yeah, sorry, that's my bad writing. I think I was saying cubed as I was I saying cubed? It doesn't matter. Yes, cubed right there. Good. I don't want to have to type in all those 0.454545454545s. Yeah? So here's what I'm going to do. Got my calculator ready to rock and roll. I'm going to instead, there's the 0.45 right in the screen. The calculator knows about the 0.45. So every time I want 0.45, I'm going to click this button that's called ANS, answer. If you've never used it before, it is handy stuff. It tells you just use the answer you just had. That is, I want x2 to be 0.45454545. So I'm just going to go answer. That is, take the last answer you got, use that. Then go subtract, and check out this numerator. Okay, you need the fancy fat calculator button. I need the answer. This is just this formula, right? Take your answer cubed. So answer cubed plus 2 times the answer. Subtract 1. By the way, if halfway through this you're like, why didn't someone tell me about this answer button before? And the answer is, I don't know. You know, that should have came up, because the answer button is really cool when you get a long decimal like this. And then the denominator is 3 times answer squared plus 2. 3 times answer squared plus 2. Let's just make sure we're clear about what's going on here. I want to do the third approximation, which would involve doing 0.454545 minus that thing I just said cubed, plus 2 times that thing I just said minus 1 in the numerator, because that's the function value. Then the derivative will be 3 times that answer squared, and that's what I pointed here, is that just use that answer above. You can't use your calculator for anything else while you're doing this, because otherwise you lose that answer thing. That's why we used to always have 2 calculators in university. One was like my one that I'm doing my calculations on. If I got to do side calculations, it's over in my little crappy calculator, right? Equals. Let me write this down. X3 equals, how can I write it down if it keeps disappearing? 0.4533 983367. You might be like, well, how do I know how long to go? I'm actually feeling pretty good after this. That 0.45 is the first 2 digits of the 0. I'm actually feeling pretty good because that stayed the same. Maybe it'll, I don't think so, but maybe it'll change, but I don't think so. On a scale of 1 to 10, 10 being joyously jumping up and down in calculus class, and 1 being actually falling asleep in calculus class, I hope you're about a 3.5. You're like, okay, so it's a shortcut to punch it in. I'm not done. You're going to jump from 3 to, it'll be awfully tempting to jump out of your seat and jump up and down after you see what's going to happen next. Because you're like, well, is this a good enough approximation? And I think on the next page they ask for a lot of decimal places. And I'm only at 2 decimal places that are good. You know, these other decimal places change, so I don't know, I'm not too confident about them. Continue using method until you get to 6 decimal places. Watch this. This is great stuff. Now I'm going to go after the 4th approximation. Fourth approximation coming up. Watch what I do on the screen. It's a technical procedure that I'm going to do here. And you got to watch, because there's a lot of steps to get the 4th approximation. Here it comes. I just pressed equals. I told it, take the answer you had and do it again. Your calculator, that's the last answer. It was 0.4533, what was it? Oops. I got to be over here. It was 0.4533983367. That was the answer. And what was on the screen said, take that answer, plus answer cubed plus 2 times answer minus 1 over 3 answer squared. No, I have the next one right there. Let me get back to you. I got to write it down. So once you get to a certain level here, I won't ask to see all that subbing anymore. I just need to see the next number. And the next number here is 0.4533 976,515. I want to write the 3rd approximation. No, I'll just go right to the 5th approximation and start to convince you that we're getting closer. Yes, question?
How did you get from 3rd to 4th again?
I just pressed equals.
Okay.
If that thing is on the screen and your last answer is right there, when you press enter, it'll do it again.
Okay, got it.
It's great stuff. Huh? Great stuff. To get the 5th answer, I just hit, I got to write them out once. I don't have to write it all out to all the subbing and everything like that. But I got to write it once to write down what I got there. Then for the fifth approximation, I'm just going to equals again. Oh, it didn't change. That's the answer. Yeah, see, if you hit equals and it doesn't change, you've got it. And it happened a lot quicker than maybe you expected. You're like, how many times are you going to have to do this? 5 is a shockingly good number of times. Because the derivative gets you so much closer to the answer, by the time you do this 3 or 4 times, you're going to be shockingly close. And if you take this number and sub it back into the original function, you'll see it'll give you something really close to 0. Is it perfect? No, because we don't know what these next decimal places are. And those next decimal places will matter. By the time you start cubing things and 2 times x squared, those type of things, it might still throw you off. So this might not give you exactly 0, but it'll give you 0 up to a shocking number of decimal places. In fact, let's try it. What was the original function? I see, this is doing this for a lot of time. Like, am I really done with this before I change what's on the screen? Because it was so nice that I could just keep hitting equals and getting more answers. And you see, it's doing something, but it's not getting a new answer because it's narrowed down as close as we can get. Okay, what was the original function? Oh, I can use the answer button again. Leave that where it is. Okay, back to here. Where's the original function? F of x equals x cubed plus 2x minus 1. So I'm going to do, take that answer. Now, cube it plus 2 times that answer minus 1. What am I expecting to get here? 0 or something shockingly close to 0. 0. The calculator has given up. It's like, well, it's not exactly 0. But it's so close to 0, I can't say anything different. It's like 0.00000000001. It's like, well, 0. Okay, 0 is the best I can do. Do you have any questions on Newton's method? It only uses the derivative, the function value, and a good guess to start off with. Are there better methods that take into account what the slope actually is? Yeah, and we will look at one of those methods in a later chapter. But this is a very good method. It worked, at least 5 guesses, that's pretty good. Question?
So we use the next value of the function as y value and the derivative.
Yeah, now let's look back at this formula. As promised, let's really take a closer look at this formula. To get your next x value, take your previous x value, and subtract whatever you get when you sub that into the function divided by whatever you get when you sub in that derivative. That will map it backwards or forwards if the slope's negative. It works out fine. If the slope's negative, it adds on instead because the sign of the derivative's in there. So if the signs are changed, it doesn't do anything. But anyway, so we can just think of it this way. It maps backwards to a better x value. And from the picture, it looks like this is going to take forever. Well, it doesn't because look at what happens to the slope. And eventually, one of the answers is going to jump really close to the answer, and then you're pretty much going to have it nailed down in a shockingly short amount of time. At first, it looks like, oh, this is going to be a lot of writing out of the 0.45s. And it can be if you don't have your calculator really figured out on what you do. And you can see now why I wrote it with formulas instead. I didn't go right to the numbers. My old video did that. I'm like, no, let's actually try and use the formulas right now and put them in like that, because then there's an easy way to use your calculator to go boop, 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 answer. Other questions? I saw another hand. Did I answer their question in the middle of it?
Yeah, I just have a question. So, like, if we use like a different number than 0.5, like 0.25, you said, and it would still like get out to a different number.
You'd still get the exact same answer. You just might get there faster or slower than other people. Yeah, and this is why I need to see these numbers. Maybe I don't actually care what your first guess is, but if I see the numbers and they head towards the answer I'm looking for, I'm like, oh, it worked out well. So you do have to write down the approximations. But what you don't have to do is write them out all those times in there, because it's going to be crazy decimals. We knew that going in because we couldn't get the answer. So it must be a crazy decimal. Yeah? So a bad guess or a not quite as good guess, it'll just happen maybe in one extra step. But still, not that many more steps. So the guess doesn't have to be that good. It works so well that a bad guess will still work well. Other questions? I'm about to wrap this up because one example is enough here. It's sort of quadratic formula type lesson in the sense that the first time you do one of these, you sort of fiddle fart around. You're like, I can't get this to work. And then by the time you do a second one, a third one, you're like, okay, I got it. It's no problem. Yeah. Newton's method can fail. It cannot work. One way it can fail is if the slope jumps you across over to a different zero. So let's just imagine that I had done a cubic like this, and I had found 2 zeros already, and now I'm working on the third one, and I'm trying to find this third zero. If I'm too far away from that zero, I might jump over and find one of my other zeros again. So it looks like it's a big problem. You know, you're like, oh, well, that's not going to work very well. But if you're actually in this situation, the answer is just get a bit better guess. Move your guess a little left or right so it doesn't jump over here like this. So the solution to this problem, I don't think it comes up in the homework. But I just want you to know that Newton's method doesn't have to work quite as efficiently as we've seen here. We might have to modify our guess a little bit. It also fails in very symmetrical situations, because you might jump over here to a new x value and then jump back to your original x value again and end up in a circle here. I got to tell you, this is the least of your worries. When this happens, you know the situation is symmetrical. There's a very good chance your answer is halfway between those two answers. So this is actually pretty nice when this happens, because it's telling you your answer is right between your two answers. That's a slight oversimplification, but it's close to true. That you don't these aren't as big a problem as you think they are. Just be aware that those are out there, that Newton can fail, and the answer to both is just get a better guess. You know, move a little left or right and find a better guess, and that should help you get your actual answer. Oh, that's it. Any questions on Newton's method?
So how would we find our first point? Like for the
There are many ways to do it, but I suggest this method to start off with, because it's probably what you're going to do anyways. When you fall into Newton's method, you're probably going to have a function that you think, oh, let's see if we can factor it. Factoring fails, and you think, well, I'm out of luck. But the information you got from the failed factoring will be enough to probably get your first guess. Yeah? In other situations, you might have a graph instead. In science, you might have a graph and go, well, I know it went to 0 somewhere in here. And that'll give you your good guess. Is the graph right from the scientific study you've been doing?
we could find x1 from a graph.
You could find x1 from a graph. You could find x1 from your subs. There are other ways, but that's basically the two ways we'll come up with that guess. Other questions? That was a good one. I encourage you to do many of these homework questions. I don't know if it's a section where you have to do all of the homework questions. Once you get the gist and you go, oh, I can make this happen, it's one of those sections. You know, other sections I'm like, you got to do all of these. This section I'm like, well, you know, you got to get the gist of it. You know, not unlike linearization. Linearization is like, make sure you can do this. Yeah.